Welcome back for the video on lesson chapter 3.6. This is over complex zeros and the fundamental theorem of algebra, which is really just an addition to what we've already been doing. So the fundamental theorem of algebra says every non-constant polynomial function with real or complex coefficients has at least one complex zero. And remember, a complex zero is a plus bi, which means it could just have the real part. It doesn't have to have the complex imaginary part. So just looking at this one here, example 1, it just says we have the h function. What is the value of the multiplicity of the zero at x equal to 0? So when x equals 0, if we just factor this here, we've got x squared factors out, and we're left with x squared minus 2x plus 1. And then we have x squared, and then this factors into a perfect square of x minus 1. So my 0 here at x squared equals 0, and it has a multiplicity of 2. And actually the 0 of 1, this x minus 1, has a 0, x equal to 1, that has a multiplicity of 2 as well. So they both have a multiplicity of 2. And this just talks about the factorization theorem says that any polynomial p with the real coefficients, all of these are, can be factored uniquely into linear factors and or irreducible quadratic factors, where an irreducible quadratic factor is one that cannot be factored any further using real numbers. The two zeros of each irreducible quadratic factor are complex conjugates of each other. Okay. So let's just see what we have here for example 2. It says we know that x equal to 6 is a 0, and we want to factor that. So it has 4 terms. We haven't really practiced any of our factoring with 4 terms yet, but we could. So I'm going to group them as these 2 terms. So x squared factors out, and I have an x minus 6, and then a plus 5 factors here, and I have an x minus 6. So x minus 6 is the common factor, x minus 6, and then I have x squared plus 5. And so this is my h of x. So this is a linear factor. X minus 6 is the linear factor. And then this is the irreducible quadratic factor. And this is the one that factors into the 2 complex conjugates. So the final factoring is really x minus 6. And then it's the zeros, I should say, are complex conjugates. So we have a 0, x equals 6, and then we have x at x equal plus or minus 5i. I times the square root of 5, plus or minus I times the square root of 5. Those are the 3 zeros. So whatever your highest leading degree is, which is 3, there is exactly that many real and complex. So there's 2 complex and 1 real. And that's basically what this linear factorization theorem tells us, that we can factor it and it has exactly n zeros if we count the multiplicities and the complex zeros. And so on the last one, they really just asked us to do this and to factor into linear and irreducible quadratic factors, and I did. And then I kept the same equation, and they asked us to factor that over the complex numbers And I did. So we have the zeros here, the one real and the two complex. So that's really example 2 and 3 are really work together. And then finding the polynomial given the zeros is similar to what we did in chapter 3 earlier in chapter 3. We know we want to have a polynomial that's a 5th degree. We also know that this is true when x is 0, the outcome is 32. And then we have zeros of -2, 4, and 1, where -2 has a 0 of multiplicity 2, and 1 is a 0 of multiplicity 2. So that must mean 4 has a multiplicity of just 1. So let's see here. So we have some p of x. We don't know what k is, but we know we have k is the, actually it's a, is the leading coefficient. We really don't know what that is, but we know that we have zeros. So x plus 2, because x minus 2 is 0. And it has a multiplicity of 2. And then we have x minus 4 has a multiplicity of 1, and then x minus 1 has a multiplicity of 2. So that's 2 plus 2 plus 1 is 5. And they said degree 5. So I'm going to multiply x plus 2 times x plus 2. And that gives me x squared plus 4x plus 4. Oops. And then I'm going to multiply this x minus 1 times x minus 1. That gives me x squared minus 2x plus 1. And then we have the x minus 4. And so P of x is x squared plus 4x plus 4 times x minus 4 times x squared minus 2x plus 1. Now we don't really need to multiply it all out. We have this a here, but we know that when x is 0, the outcome is 32. So let's just pretend a equals 1, and we're going to do the bare minimum case here. So if x is 0, then we have 0 squared plus 4 times 0 plus 4 times 0 minus 4 times 0 squared minus 2 times 0 plus 1. So 30, we're going to solve for a here. So 32 equals a times 4 times a -4 times 1. So 32 equals a -16a. So a must be a -2. So P of x equals a -2 times x squared plus 4x plus 4 times x minus 4 times x squared minus 2x plus 1. And like I said, you could multiply that all out. It would be x to the 5th. Let's do that just for fun. So I'm going to bring my 2 up front, and let's do these here. So we have x cubed plus 4x squared plus minus 16x. And then minus 4x squared minus 16x. Okay, x squared plus 4x squared minus 16x. And then minus 4x squared minus 16x minus 16, all times x squared minus 2x plus 1. So let's simplify in here first. X cubed, and the 4x squared and the minus 4x squared cancel out. And then we have minus 32x minus 16 times x squared minus 2x minus 1 plus 1. So this is going to be 9 products because we've got 3 terms times 3 terms. So we have p of x equals negative 2 times x to the 5th minus 2x to the 4th plus x to the 3rd minus 32x squared to the 3rd minus 64x squared minus 32x minus 16x squared plus 32x minus 16. Negative 2 times x to the 5th and then minus 2x to the 4th and x cubed times x cubed minus 32x cubed leaves us with just a minus 31x cubed. And then we have a negative 64x squared and a negative 16x squared. That's a negative 80x squared. And then the 32s cancel out, and then we have minus 16. And of course, we could distribute this too. That's a big polynomial. Touch me back for the last lesson in chapter 3.